This particular section is listed in Chapter 6, but if you look it up in the book, it's actually Chapter 7, Section 7, Indeterminate Forms and L'Hopital's Rule. It looks kind of like L'Hopital, but it's L'Hopital's Rule. And L'Hopital was this kind of rich guy who had a really smart teacher. And L'Hopital, I guess legend has it, they kind of made a deal with his teacher, Bernoulli, indicating that Bernoulli came up with this cool idea, but let me have credit for it and I'll give you some money. And that's pretty much how legend has it that L'Hopital published this particular rule for calculus for finding the limit of what we call of an expression that gives us an indeterminate form. Now, one of the very first limits that we looked at that was a special limit was the limit as x goes to 0 of the sine of x over x. And as you just use direct substitution, you get 0 over 0, and this is an indeterminate form. Okay? So what we did is we made a table of values, and then later I mentioned to you the squeeze theorem as a way to prove that this particular limit turned out to be equal to 1. Now, we had other limits that gave us indeterminate forms, stuff like this, where we did an algebraic trick, or stuff like this, where we did an algebraic trick to try to evaluate them. This one would use direct substitution, would give us 0 over 0. This one would give us infinity over infinity. And both of these are indeterminate forms. There are 7 different kinds of indeterminate forms. But these two especially are the two that could pop up in the AP, so I want to make sure that you understand how to go about to solve this. So we used L'Hopital's rule. It was written by John Bernoulli. There's a whole slew of Bernoullis that were very famous mathematicians back in those days. And it was L'Hopital, who was the French mathematician, credited for writing the first text on differential calculus, and therefore brought in this L'Hopital's rule. And L'Hopital's rule says, let f and g be functions that are differentiable on an open interval a, b containing c except possibly it's c itself. Assume that g prime of x doesn't equal 0 for all values of x in a, b except possibly it's c itself. And if the limit of f of x over g of x as x approaches c produces an indeterminate form, we just substitute in, and we get an indeterminate form like 0 over 0 or infinity over infinity. Then, as it turns out, the limit as x goes to c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x, provided the limit on the right exists. That means this limit. So what that means, this limit, excuse me, on the right, my other right. So what this is saying is, hey, we can find this limit even if we get 0 over 0 if we use L'Hopital's rule, take the derivative of the numerator, the derivative of the denominator. Now, this is not the quotient rule. It's not low d high minus high d low over the square of what's below. You just take the derivative of the numerator, the derivative of the denominator, and if this limit exists, so does this one, and it's the same value. And as I mentioned before, this works whether it's 0 over 0 or infinity over infinity. Now, infinity over infinity can be positive infinity over positive infinity, negative over positive, positive over negative, negative over negative. They all still work. So we're going to try some examples where we're going to evaluate some limits using L'Hopital's. But remember, you can only use L'Hopital's if you get one of these indeterminate forms. So let's start right here. This limit as x goes to 0 of e to the x minus 1 over x. Now notice, if I plug 0 in here and here, I get e to the 0, which is 1, minus 1 is 0 on top, 0 on the bottom. So my suggestion is apply L'Hopital's rule here. Now, this is my notation. This is not standard notation. I wouldn't use this on the AP test, but to show that you're going from this step and you're going to apply L'Hopital's rule, put a little capital L with a circle above the equal sign. So that tells me you're applying L'Hopital's. And I take the limit as x goes to 0 of the derivative of the numerator, which is e to the x, all over the derivative of the denominator is 1. Now, as x goes to 0, notice I can use direct substitution here. I do not get an indeterminate form. I get e to the 0, which is 1 over 1, which is 1. Okay? And here's another one. If I let x go to infinity, the natural log of bigger and bigger and bigger and bigger and bigger numbers gets big. And the denominator x is getting big, so I have infinity over infinity, which is an indeterminate form. So I apply L'Hopital's rule here. It works for 0 over 0 or some kind of infinity over some kind of infinity. And I get the limit as x goes to infinity of, well, the derivative of the natural log of x is 1 over x, and the derivative of x is 1. So I have the limit as x goes to infinity of 1 over x. Well, as x goes to infinity, my denominator is getting bigger and bigger and bigger without bound, so this is going to be 1 over really big, which approaches 0, and so the limit is 0. Here's another example. If I use direct substitution here, I get positive infinity e to the x positive infinity. I get positive infinity over positive infinity. So to solve this limit, I'm going to use L'Hopital's rule, and I'm going to take the derivative of the numerator and the denominator. Well, the denominator is easy anyway. So the limit as x goes to infinity, that would be 2x all over e to the x. Well, as x goes to infinity, this gets big. I still have an indeterminate form. So you say, well, does it mean it doesn't exist? No, it means since it's an indeterminate form, I can apply L'Hopital's rule a second time. Sometimes I even have to apply it a third time. Not on this one, though. This is the limit as x goes to infinity of 2 all over e to the x. Well, now as x goes to infinity, this stays at 2. This gets big without bounds, so 2 over big goes to 0. Kind of slick. And of course, this is everybody's favorite here. This is the one that we already know what the answer is. The answer is 1. Let's use L'Hopital's rule and show that. So I take the derivative of the numerator, which is the cosine of x, all over the derivative of the denominator, which is 1. And as x goes to 0, the cosine of 0 goes to 1. So this is 1 over 1, which is 1, which is what we said way back in chapter 1. Now, there's more to L'Hopital's rule, as there are 7 indeterminate forms, and here are the other 5. 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, or infinity to the 0. All of these are indeterminate forms. We can't tell what they're equal to. I mean, we might think they're 0 or 1 or something, but we can't actually determine that. So what we would have to do is use a variation of an approach involving natural logs and natural exponential functions, and to set this up so that we can somehow get to a point where we can apply L'Hopital's rule. But we don't have to worry about these 5. We do need to worry about these ones where we get 0 over 0 or infinity over infinity. Now, if you get 0 over infinity, that's not an indeterminate form. That's 0. So don't think that you can apply L'Hopital's rule any time that you have some limit. It has to be an indeterminate form. So, it'd be a good opportunity to practice some problems there. This is again from section 7.7.